Hi everyone, welcome back. Today we're going to be talking about exponential functions and their derivatives. So we are still in the chapter of inverse functions, and when we're dealing with these exponential functions, we want to make sure that we establish these definitions and these properties for these exponential functions that we have seen before. On screen here, on the left-hand side, you have the more brief definition of a function that is an exponential. So all we have to do is verify that we have some base, which we'll call b, that's raised to the power of x, where in this case, x is the variable. Now, there are some restrictions here that b must be greater than 1, and so we'll go ahead and write those, that b must be greater than 1. Okay. Oh, excuse me, sorry. B actually has to be greater than 0, and b cannot be equal to 1. As long as those conditions are met, we will have everything that we need for this exponential function. These exponential properties on the right-hand side of your screen are the exponential properties that we've discussed in college algebra or pre-calculus or algebra 1 or algebra 2. That's where we've seen these before. Now, we want to talk about more specifically how we are going to work with these exponential functions and how we're going to be associating calculus to these exponential functions. So in order to start that discussion, we're going to briefly extract this exponential function b to the x. B to the power of x we can actually attain if we take the limit as r is approaching x. So as r is approaching x, we have for the function b to the power of r. Now remember, b to the power of r, this is the function that we are initially looking at. And then we start looking at all of the values that start approaching this value, which is x, as they get closer and closer and closer to x. Since e to the power of x, or in this case b to the power of r, is an exponential function, it's going to be smooth and it's going to be continuous, which means we just get b to the power of x. Now, we also have some other definitions that we are going to be working with. And here briefly we're going to go ahead and state them. The first one is going to say that if b is greater than 1, then the limit as x approaches infinity for b to the power of x, we attain the limit of infinity, or it just grows without bound. And I'll give you a visualization of this in just a little bit. And we also get that the limit as x is approaching negative infinity for b to the power of x, we should attain 0. Now, how did this come about, or how do we look at this? Well, I will give you a visual really quickly. So here I have this screenshot from GeoGebra. And this function here is an exponential function that has a base that's greater than 1. Notice as your x values are approaching infinity, so as these x values keep moving to the right of this axis, notice what your overall function is doing. What are the outputs? That means that as x gets large, so does the outputs, which means there is no stopping point for those outputs as long as x keeps going towards infinity. They don't taper off at any point in time, and that's how we attain infinity, as this part of the limit. Now, as x heads towards negative infinity, Well, if x is heading towards negative infinity, that means we are approaching this function value we're approaching this function value as x keeps increasing towards the left-hand side. Now, as that happens, these function values keep getting smaller and smaller and smaller and smaller, and they keep on converging to a y value of 0. And that's where we get this portion of the limit, that as the limit as x approaches negative infinity for a function b to the power of x, we must get 0. And again, this is so long as we have a base value that is greater than 1. Let's look at a different one. Well, what if the b value is between 0 and 1? In other words, it's a fractional value. Well, then we can take, we can take and consider then a limit as x is approaching infinity for b to the power of x. This is going to be 0, and a limit as x is approaching negative infinity for b to the power of x. This is going to get us infinity. Now, again, how does this come about and how do we visualize this? Well, again, I have a graph for that, which I will show you in just a bit. Here we are. So if we have an exponential function with a base that's in between 0 and 1, then what we have here is we have an exponential function that looks like this. It's still concave up, however, as x heads towards infinity, so as these x values keep getting closer and closer and closer to infinity, in other words, they keep getting larger and larger and larger, that means that our overall function output is going to get closer and closer and closer to 0. And conversely, if x is getting large in the negative direction, so x is approaching negative infinity, our y values, or in this case our outputs, are getting larger and larger and larger. So that's going to mean that we're approaching infinity. And again, we have to make sure that we analyze these exponential functions and that we use this process of these exponential functions in order to try to extract what are these limits that we are going to be observing. So let's go ahead and let's see if we can work with a few limits. That way we can start moving on to something a little bit more difficult. So here goes. We want to find the limit. For part A, we're going to have the limit as x tends to infinity for e to the power of 2x minus e to the power of negative 2x, all divided by e to the power of 2x plus e to the power of negative 2x. There we are. So this is one of the first examples that we are going to be working with. Now, there might be different approaches for an example like this. And what I want you to do is I want you to really quickly just analyze this example and try to process it. What is it that we're looking at, and how are we going to interpret what we're looking at? All right, so I want you to think about that for a few seconds. All right, so now that you've familiarized yourself with this example, we're going to try to give this a shot. Now, I am going to say that oftentimes when you're doing math, or in this case when you're doing calculus, sometimes the only way to know if you're on the right track is to actually go on that track and figure out what it is that you need to keep doing or that you're doing. So In this particular case, what I want to do is I want to multiply both numerator and denominator by e to the power of negative 2x. So I'm multiplying here by e to the power of negative 2x. When this happens, I now get the limit as x tends to infinity, distributing, then e to the power of negative 2x multiplies e to the power of 2x. That means their exponents are going to add according to this property that we have right up top, this first property, which then means that that is going to be e to the power of 0 minus multiply this numerator, so e times e, but the bases are the same, that's e, so I add the numerator, so I add the exponents, which becomes negative 4x, all divided by, same thing in the denominator happens, e to the power of 0 plus e to the power of negative 4x. And this is actually where I want to be, specifically because now e to the power of 0, that's just 1, minus this, this term here is now 1 divided by e to the power of 4x, all divided by 1 plus 1 over e to the power of 4x. So analyzing this now, we can then see that as x tends to infinity, well, x is going to tend to infinity here on the numerator, but since this is a complex fraction, this denominator, e to the power of 4x, is going to get really large. That means the overall fraction is going to tend to 0. The same thing is going to happen in this big denominator, where this fraction is going to tend to 0. Which means once we apply the limit, those two terms, they go to 0, which means we're only left with 1 divided by 1, which in this case is just 1. And that's the limit. Nothing else to it. Nice. So let's go on to part B then. Part B, I want to work with a limit as x tends to infinity for the function of e to the power of negative x squared. Okay, let's go through this process. Once again, we have to start looking at this and we have to then start analyzing. We can rewrite this in this way to say that this limit as x tends to infinity will be for 1 divided by e to the power of x squared. Now as x tends to infinity, well, that means this x is going to go to infinity. That means e to the power of very large numbers is going to get you something very large, which means the overall denominator is growing exponentially. That means the overall fraction is going to get very, very small, and that's going to tend to 0. Which means once we apply the limit, we then get a limit of 0. And that's it. That is how we start looking at these exponential functions and their limits. So, we then want to start extracting a little bit more. We want to start identifying certain aspects for these functions. So what I want to look at here is I'm going to work with a function f of x, and let me do this in a different color that's not green, blue, or black. So let me do this in this pink type of color. So I'm going to let f of x equal to e to the power of x. Awesome. Once this happens, what I want to do is I want to consider the derivative now. So consider f prime of x. Well, f prime of x, what does that look like? Well, if we go back to Calc 1, the definition says that we must have the limit as h is approaching 0 for the function of f of x plus h, which means that is going to be x plus h, minus f of x, which in this case is just e to the power of x, all divided by h. Now that portion, I'm going to say recall the definition of a derivative. That definition of a derivative, if we said let f of x be a continuous function, continuous differentiable function, then the definition that we get, there was actually two definitions, but we're going to focus on one of them right now. We get f of x plus h minus f of x all divided by h. And that was actually your difference quotient back from college algebra or from algebra 2. So back to the one at hand here. Now, given this limit definition, what we can do is we can rewrite the numerator as e to the power of x multiplied by e to the power of h. Because they have the same base and their exponents are being added, that means that we can multiply by the exact same base, and that's minus e to the power of x all divided by h. Notice the numerator. The numerator can now factor out, which means the numerator is just e to the power of x multiplied by e to the power of h minus 1 all divided by h. That's looking really good. Now, the limit here is only being applied to these h values. So, as the limit is approaching 0, the h values are the only ones that are being affected by that process. So, e to the power of x is treated as a constant with respect to this limit. So we're actually looking at e to the power of x multiplied by the limit as h approaches 0 for e to the power of h minus 1 all divided by h. Now the big question is, what is this limit? Well, in order to answer that, we're going to need a visual. So I'm going to go ahead and post a visual here in just a few seconds. All right, here we are. We have the visual here, and this function here is e to the power of x minus 1 divided by x, which is this function here in the parentheses, minus the whole variable aspect that x becomes h. Overall, same process. However, as your h values, or in this case, as your x values tend towards 0, so as we keep getting closer and closer and closer to 0, from both sides of this function, that means that my function is approaching one output. And that one output, or that one y value, is 1. Which makes this calculation here really nice then, because we now get e to the power of x times this limit of the function, where that limit of the function as h is approaching 0 is just 1. Which means, what do we get? Well, we just get e to the x. And that's really nice, because now, at the end of the day, we get to see that if we consider the function to be e to the x, and then we take its derivative, then we naturally just get the function itself. So as we start applying these derivatives for exponential functions, we have to be very, very cognizant of how it is that we're taking those derivatives, because if we're taking the derivative of e to the power of x, then we just naturally get back e to the x. The derivative of the function is the function itself. It's one of the unique functions that does this in math. So let's go ahead and let's start summarizing what we have so far. So what we have so far says that if we're looking at the derivative with respect to x for a function e to the power of x, then the derivative of that function is just the function itself, just e to the power of x. Now, we can have a chain rule. Well, the chain rule says that if we take the derivative with respect to u for this function e to the power of u, then what we have is e to the power of u multiplied by this chain rule process where we need to take the derivative of u with respect to x. So that means we're going to multiply by the derivative of u with respect to x. And again, this is where u is equal to some function of x. All right. So this is how we are working with these derivatives of these exponential functions. And what we're going to do is we are now going to start applying some of these processes that we've learned, not only in this course, but in Calc 1 as well. We are going to start applying the chain rule, the product rule, the quotient rule to these derivatives. That way we can familiarize ourselves with these derivatives of exponential functions. So we are going to work on a few examples here. So what we want to do is we want to differentiate the function here. So differentiate the function. Part A. We're going to have f of x is equal to e to the power of x plus x to the power of e. So if you want to take an approach to this, by all means, you can put pause on the video and then go ahead and start the process. If not, I will work it out in just a bit. Now, taking the derivative here, I'm going to apply the derivative for this function. So I'm going to take it step by step. Applying the derivative here implies that I'm going to differentiate this function with respect to x. This then will say the derivative with respect to x for e to the power of x plus x to the power of e. In order to do this, my derivative property says that since I have two terms that I'm differentiating, I can distribute, or in this case, I can differentiate the terms individually, which means f prime of x, I need to take the first derivative, or I need to show that I am going to take the first derivative, plus the derivative for the second function. There we are. Let's write that a little better. There we are. Now, the first term is just applying the properties that we just learned. So the derivative of e to the power of x with respect to x will just be the function itself, e to the power of x. However, the second derivative, I want you to pay attention here, or I want you to focus on this a little bit more, simply because x is the base of the variable that we are differentiating. And we have an exponential, or we have an exponent that is a constant. In this particular case, the exponent is not a variable. So the rules that we just developed within the past few minutes do not apply here. only the power rule applies, and that power rule we learned back in Calc 1. Well, how do we take the derivative of this variable that has a base, x, and a constant e? Well, we use the power rule where we drop the exponent forward, and then subtract 1 from that exponent. And there you have it. That's it. That's your derivative. We found the derivative. That's it. Nothing more, nothing less. So that's pretty good so far. Let's keep going. Let's go to part B. Part B, we want to work with g of x is equal to e to the power of x squared minus x. Okay, so when we're looking at this here, once again, we are going to go through the whole properties of these derivatives. So I'm going to take it step by step. Taking the derivative for g of x will be denoted as g prime. However, on the right hand side, I need to show that I'm taking the derivative with respect to x. In this case, this is going to be e to the power of x squared minus x, as such. Now, what this tells me is that I have what is known as function composition here. In other words, what I'm doing is I am using my chain rule process. I need to take this derivative for this function with respect to x, but this function is comprised of two different functions. One easy way, or sorry, not easy, but a better way to look at this is if you're looking at e to the power of u, where u is equal to x squared minus x. So again, if you were to compose these two functions, you would then see plugging in u into this function, into e, you then get e to the power of x squared minus x, which is this function. So let's keep going with the derivative. The derivative of e to the power of some function is just itself, like we see over here in the chain rule, which means this is just e to the power of x squared minus x. And now we get to multiply by the derivative of the inside function. Well, looking at the derivative of the inside function, that's going to be the derivative of x squared minus x. And again, that's part of the chain rule. In doing so, we're going to clean this up. This is e to the power of x squared minus x multiplied by this derivative. So what is that derivative? Well, x squared, that's going to be 2x minus x. Take that derivative, it's just minus 1. And here you are. There is your answer. Nice, neat, and concise. Awesome. We're looking pretty good so far. So what I'm going to say is, let's keep going. Now that we got part A and part B down, let's start increasing the difficulty just a little bit more. Just a tad bit more. Part C. For part C, I want y is equal to x squared times e to the power of negative 1 over x. That's what I want to look at. So again, if you want to try these examples before we work them out in class, by all means press pause on the video and try them yourself. Alright, so when we want to take this derivative here, I'm going to apply the derivative. So this is going to be the derivative with respect to x for this function y. On the right hand side, again, I'm taking that derivative, so derivative with respect to x for x squared times e to the power of negative 1 over x. There we are. So on the right hand side, I will need to apply the product rule, and I have to keep that in mind. So when I'm doing this, this is going to be dy dx, the derivative for y with respect to x. Now, applying the product rule, that's going to mean that I need to do the derivative of the first function. So I'm going to write this step by step. The derivative of the first function multiplied by e to the power of negative 1 over x. So derivative of the first multiplied by the second plus the second function, the first function, x to the power of 2, multiplied by the derivative of the second function, which is e to the power of negative 1 over x, as such. Alright, that's looking pretty good so far. Now, we are going to go ahead and apply the derivative. So the derivative of x squared with respect to x, that is going to give us 2x multiplied by e to the power of negative 1 over x plus x squared multiplied by this derivative. Now, if you're following along, then the derivative of this exponential function is a function composition, which means that we need to apply the chain rule here. So, applying the chain rule, this says that when I take the derivative of an exponential function, I just get the exponential function back itself. So this is a derivative applying here, getting the function back itself, the exponential, multiplied by the derivative of the inside function. And that's a derivative of negative 1 over x. Now, how do we do the derivative of 1 over x? Well, for that, I'll do it over here. This is going to be the derivative of, let's say, negative x to the power of negative 1. Taking this derivative, negative comes out to the front, or you can just leave it there. Taking the derivative, drop the exponent forward, so that's now going to be negative 1 times negative 1, which just gets us a positive. Subtract 1 from the exponent, which gets us negative 2, which is really nice because now we just get 1 over x squared. So as we start looking at this derivative here a little bit more completely, 2x times e to the power of negative 1 over x plus, then we have x squared multiplied by this new derivative, this 1 over x squared, e to the power of negative 1 over x, and then multiplied by 1 over x squared. That was that derivative that we found here. Then we can see this derivative cleans up a little bit more. Now, some of you might be saying, yeah, that's a lot of work to keep simplifying, but in calculus, we have to make sure that we simplify as much as we can, just in case that we need to take another derivative. So be very mindful of that. Negative 1 over x. The x squareds here are going to cancel, and we're left with we're left with e to the power of negative 1 over x. And that's all. That's all there is to it. Awesome. So what I want to do at this point in time is I want to then start looking at a different function. Let's look at part D. I am going to move this over. Let's say move it right there. There we are. All right, that looks pretty good. So I'm going to work with part D. Part D is going to be f of t is equal to tangent of 1 plus e to the power of 2t. There we are. All right, not bad. So what we need to do at this point in time is we need to take a derivative for a trigonometric function. Now, the derivatives of trigonometric functions are the derivatives that you should have seen back in Calc 1. And what we're going to do is we're going to make sure that we keep using those derivatives in this course. That way we can keep on familiarizing ourselves with those derivatives. So let's go ahead and let's get started here. As I'm taking this derivative, I'm going to apply the derivative here, f of t. This is going to be the derivative with respect to the variable t for the function tangent of 1 plus e to the power of 2t. Awesome. So, as I'm looking at this, I now need to figure out, okay, well, what's going to be the derivative of tangent? Well, if you recall back from Calc 1, the derivative of tangent, and I'm going to write that here, the derivative of tangent, let's say with respect to theta, tangent theta, is going to be equal to secant squared theta. What that means for us is that when I take the derivative for this tangent, it's going to be secant squared, so secant squared of its argument, which is 1 plus e to the power of 2t. And since its argument has another function, that means that we still need to apply the chain rule here, which means I still need to take the derivative for this function, 1 plus e to the power of 2t. Okay, let's keep going. So that's still going to be secant squared secant squared of 1 plus e to the power of 2t. Taking this derivative here now, the derivative of 1 with respect to t is just 0, and the derivative of e to the power of 2t, this is going to use another chain rule, where once we apply that chain rule, we get 2 times e to the power of 2t. So cleaning all this up and making it look nicer, f prime of t is going to get us 2 e to the power of 2t multiplied by secant squared of 1 plus e to the power of 2t. And here you are. That is your derivative. Sorry, I forgot to circle this other one. So there we go. We have 4 examples where we used a variety of different rules when we talked about derivatives. Awesome. Now, what we want to do is we want to talk about its antiderivative, or in other words, if we want to take an integral. So let's start looking at that. So if we have given to us a function which is e to the power of x, then when I take its derivative, we just get e to the power of x itself. However, if we want to apply the fundamental theorem of calculus, the fundamental theorem of calculus says that if we're going to apply its derivative, or its antiderivative, with respect to x, then when we look at this, the antiderivative for its derivative of that function, we naturally just get the function f of x back, right? We're undoing its operation. On the right hand side, this means that we need to take the antiderivative for e to the x, and that's exactly what we do. We take the antiderivative for e to the x. However, we have to be very careful, because anytime that you take that antiderivative, wow, I don't know what happened there. My apologies. Apparently the computer said, hey, you need to zoom out as much as possible. Wow. Okay, there we go. Back at it. There we go. Sorry about that. So now we just need to account for a possible constant that was taking place here. So when we're looking at antiderivatives for these functions, we always have to make sure that we account for those constant values. And we're going to work on that in the next example. So in the next example here, we want to evaluate these given integrals. So evaluate the integrals. Part A is going to be the integral for x squared times e to the power of x cubed dx, just like this. And again, we have different methods that we learned back in Calc 1. The different methods that we learned back in Calc 1 to evaluate these integrals was that we could either try to simplify, we could try to use a trigonometric antiderivative, or we could use substitution, or we can use a straightforward power rule. In this particular instance, since it looks like I have function composition here, where I have e to the power of x cubed, what I want to do is I want to proceed with that substitution. So I want to keep going with this, where we have u is equal to the power of x cubed. Now, using substitution then, I need to find the derivative, or those differentials that I will be working with. That means that du is going to be 3x squared dx. So now we kind of see x squared dx happening here, but we don't see that 3, which means we're going to divide by 3 onto both sides. And now we can see that substitution take place. This x squared and this dx now becomes 1/3 du, and the x cubed initially becomes u. So this new integral becomes the integral. We no longer have x squared and dx, but we do have e to the power of u multiplied by, and this is now going to be this x squared dx. X squared dx is that 1/3 du. That 1/3 du. Very nice. Now we're going to apply some of our properties that we learned back in Calc 1. 1/3 is a constant, which means it can move straight through the integral, and now we have e to the power of u du. So all we need to do is find this antiderivative. Let's find that antiderivative then, or that integral. Well, the antiderivative for e to the u is just e to the u itself. So this is going to be e to the power of u. Now we took an antiderivative, and this is an indefinite integral, which means we need to add a constant. Let's distribute, and once we distribute here, let's go back and resubstitute, because at the end of the day we were trying to evaluate the integral with respect to the variable x and not the variable u. So my answer must not have the variable u in it, it must have the variable of x. So this is going to be 1/3 multiplied by e to the power of x cubed plus the constant c. And that's our final answer. Not too shabby so far. Looking pretty good. Let's keep going. Part B. Part B, we're going to evaluate the integral of 1 plus e to the power of x quantity squared divided by e to the power of x. All right. So let's go through and let's try to see what kind of substitutions we could make, if any, and then we can go from there. As I'm looking at this, I don't think I want to do a substitution, simply because substitutions look like it might, oops, I forgot my dx here. My apologies. Substitution looks like it might go a little bit astray. So I want to kind of avoid that substitution. Instead, what I want to do is I kind of want to expand that numerator. I like where that numerator is going, so let me finish that thought process in expanding it. So expanding that numerator, we get 1 plus 2e to the power of x plus e to the power of 2x, all divided by e to the power of x, and this is all with respect to x. Now, because the denominator is a single term denominator, I can then break my fraction into 3 individual pieces. The first one is 1 over e to the x. The second is 2e to the x divided by e to the x, and the third term is going to be e to the 2x divided by e to the x. And this is all with respect to dx. Now that I have this, I can rewrite the first term as e to the power of negative x. The second term actually simplifies just to 2. And the third term, if we subtract the exponents because the same bases are being divided, we get 2x minus x, which is just e to the power of x. Look at that. That looks really, really nice. And that is something that I wouldn't mind integrating there. So now I can go through and I can figure out this integration. Well, what is the integral of e to the power of negative x? If you're having trouble with that, that's okay. Make a quick u substitution for negative x. And in that case, it would be e to the power of u, and then proceed the exact same way as we did in part A. You should arrive at the conclusion that that first term integrates to be negative e to the power of negative x. The second term, integrating 2, will get us 2x. And integrating the last term is going to just get us e to the power of x. What are we missing? Since this is an indefinite integral, we're missing a constant plus c. Wow, those things are beautiful. There we are. Part C. Working with part C, we're going to work with a definite integral. That means we're going to be given bounds. I have in the numerator the square root of 1 plus e to the power of negative x, all divided by e to the power of x with respect to dx. Now again, you have different approaches. Like we did in part A, we could try to make a u substitution, or like we did in part B, we could try to simplify somehow, some way, using algebraic techniques. At this point in time, I would venture to say that we probably want to make a u substitution. And that's what I'm going to carry on with. I'm going to say that u is going to be equal to the radicand. That means everything inside of that radical. So we get 1 plus e to the power of negative x. What is now du? So du is now the derivative for this function. So that will then get me negative e to the power of negative x, and this is going to be dx. Now, what does e to the power of negative x look like? Well, let's do a couple things. First off, the negative that's multiplying e to the power of negative x, let's divide that over to the other side. So we're looking at negative du. Secondly, a negative exponent requires us to take the inverse, so we're looking at 1 divided by e to the power of x, and this is dx. And the reason I want to do this is because now, on my original integrand, I see that my denominator has e to the power of x, which I have here in my differential, and I have my dx and my dx. So naturally, this then starts becoming real nice. For now, I will leave the bounds empty for this integral. However, I have the square root of u. That was my substitution. divided by, in this case, I have 1 over x dx. That's now going to be negative du. So I don't have a denominator here, so let me go ahead and clean that up. I don't have a denominator anymore, square root of u. But I now have my negative du. Now I need to work with my bounds. And working with my bounds, I need to go ahead and think about how I'm going to re-index these bounds, or change my bounds of integration. So in this particular case, what I'm going to do is I'm going to make my substitution for these values. So I want you to notice here. Let's work with different colors here. That way, hopefully, we can see what is taking place. I am going to work with, let's see, I already got green. I'm working with blue. I got black. So let's work with orange color here. So this orange color, what I'm going to do is I'm going to figure out that this bottom 0, this lower limit of integration, was with respect to x. That means that x here was equal to 0. Well, what does that mean for u? Well, that means for u, when we have 1 plus e to the power of negative x, x needs to be 0. What do we get here? Well, we naturally just get 1. Which means when x is 0, my lower bound, or my lower limit of integration, under that substitution is now just 1. Okay, let's work with the other one. Let's make this in red. Upper limit of integration, this was x is equal to 1 initially. So when x is equal to 1, I'm going to make that substitution in my original substitution here. So that now says 1 plus e to the power of negative that x value, which is 1. What do we get? Well, we get that itself. We just get 1 plus e to the power of negative 1. If we could simplify, we would. In this case, we cannot, so we leave it as is. Let's keep going. So there's a negative on that du. That's going to factor through. So that's going to be negative 1, then 1 plus e to the power of negative 1. Square root of u, I can rewrite that as as u to the power of 1/2, and this is going to be with respect to du. Looking good so far. Let's keep going. Now, I want to integrate u to the power of 1/2. So let's go through that integration. Going through the integration, u to the power of 1/2, this is then going to tell me that I'm going to add 1 to the exponent, so 1/2 plus 1, and then I need to divide by that new exponent, that 1/2 plus 1. All right, looking good. Then I'm going to need to evaluate that from 1 all the way to 1 plus e to the power of negative 1, and we'll see what we get. Let's keep going. Here we go. Numerator, that's now going to be u to the power of 3/2. Denominator is 3/2, but that's whoa, sorry, that was my dog there coughing. So divided by same denominator, 3/2. There we are, and we're going to keep evaluating this from 1 to 1 plus e to the power of negative 1. Let's keep going. Complex fraction, we then get negative 2/3 multiplied by u to the power of 3/2, evaluated from 1 all the way to 1 plus e to the power of negative 1. Looking good. Let's make that substitution now. Or, sorry, let's make that evaluation. Not a substitution, but that evaluation. So, negative 2/3 multiplied by 1 plus e to the power of negative 1 raised to the power of 3/2 minus, and again this has another minus, so minus and minus, that's going to be a plus. That's going to be 2/3 multiplied by 1 to the power of 3/2. It's not looking bad. All right, it's looking pretty good there. Oh, whoops. My apologies. I believe I got this incorrect. Wow. See, this is why I miss being in class, because in class somebody would have probably pointed this out. Now, I caught my mistake here, and the mistake happened here, where I'm assuming that 1 plus e to the power of 0 is 1. In that case, it's incorrect, because this is really 1 plus 1, which is not 1, it's actually 2. Which means this 1 needs to become a 2, this 1 needs to become a 2, this 1 needs to become a 2, this one becomes a 2, this one becomes a 2, and finally I make my change in here where we have a 2. My sincerest apologies, everybody. We're all human, we all make mistakes. We learn, and then we move on. So, here we go. Now, evaluating 2 to the power of 3/2, so 2 to the power of 3, that's going to get me 8, and then the square root of 8 is going to get me 2 times root 2, but I already have a 2 out here, so that's going to be 4 root 2 over 3. Awesome. Minus this first part here, which is 2/3, multiplied by 1 plus e to the power of -1 to the power of 3/2. We can't simplify any further, hence we are done. That is it. Awesome. So what I want to do is I want to work on one more quick example, and that last quick example is going to be an application problem that we have for these rates of change when we're working with these exponential functions. So I'm going to take some time, I'm going to write that problem down. If you want, you can review what you have written down so far, or if not, then by magic of the internet, the word problem will appear in just a few seconds. Okay, so magic, here it is. A bacteria population starts with 400 bacteria and grows at a rate of this function given to us, which is r of t, is equal to 550.268 multiplied by e to the power of 1.12567 t bacteria per hour. So the question becomes, how much bacteria will there be after 3 hours? So one important aspect that they're giving us here, and I'm going to highlight this, one important aspect is that they're actually giving us that the bacteria, what the bacteria growth rate is. So they're giving us the rate of growth. Oops, let's go ahead and highlight this. Here we go. So they're giving us the rate of growth. So again, what they're giving us is they're giving us that derivative, which means if they give us a derivative and the question is asking how much bacteria will there be after 3 hours, that means that we need to undo that derivative. In other words, we need to find this antiderivative. So what I'm looking at so far, or better yet, what I'm interpreting so far is this, that if they're giving us r of t, then I need to integrate r of t with respect to t, and this in turn will then get us the amount of population of bacteria. So this will get us a certain amount, and we're going to call this just a different function. Let's call it n of t, just for simplicity. So the thing that we now have to worry about is this, that when we're looking at this integral, we then want to figure out how much bacteria is there after 3 hours. Well, if it's growing at that rate, then we could integrate from 0 to 3, assuming that 0 is going to be our baseline in which we start observing that bacteria. Not only that, when we integrate, we should have a constant as well. But for us, that's going to present itself in a smaller issue. that smaller issue says that the bacteria doesn't start at 0. The bacteria actually begins with 400 bacteria. So when we start looking at this, and we start looking at this integral, here we are, and we start looking at this integral, we're going to start making some changes. Those changes are as follows: that if I want to find out how much bacteria this particular culture has, after 3 hours, my time needs to be at 3 hours as such. I start off with 400 bacteria as my population, and then we move through that rate of change. That way we can calculate its antiderivative, and in that sense, we're going to be able to capture how much bacteria is in that culture. 567T. There we are. All we have to do is work with the integration here. This integration, all you have to do is make a u substitution. And I will leave that up to you so that you can verify. So, once we have this, we will be estimating that there is 11,713 bacteria within that population after the 3 hours. So let me summarize this. After the 3 hours, the bacteria population will be approximately 11,713. And that's all there is to it. This now concludes this section for exponential functions and their derivatives. So I hope you all enjoyed the lesson, and I will see you all for the next one, where we will talk about logarithmic functions and their derivatives. Until then, have fun.